Assalamu alaikum dear friends. I hope all of you will be fine. Today we will talk about some other topics in probability and random variables. So before diving into the other topics, I want to solve some questions related to the independent of events. Okay, so therefore I am using a book today. I'm not using any slide but a book today. So this is example 2.34, and the question here is that suppose a fair coin is tossed 3 times and we observe the resulting sequence of heads and tails. Okay, a coin is tossed 3 times, and this is basically a sequential experiment in which a coin is tossed first and then second time and third time. Okay, so in this question you have to find the probability of elementary events. In this toss you might have heads, tails, heads, tail, heads, tail, heads, tail, heads, tail, heads, tail, head, tails, tails, and tail, tail, tail. In these 3 turns you might come across these 8 outcomes. So the first step in solving any probability related question is to write a sample space of the related events. Okay, so what are the events here? This is basically a sample space and we have to write all the elements in this sample space. Okay, in this question you have to find the probability of each event. How can you find it out? You can find it out by using the again a very straightforward rule that the number of elements in a specific event divided by the total number of elements in a sample space. This is the formula and you can write it like this. But there is another formula, and that is related to the independence of events. Okay, here you can see that in a coin toss either you can get heads or tails, and getting heads or tails are basically independent of each other. If you toss a coin and you get heads, okay, so in second toss, in second step, or in second turn when you are tossing a coin, the results of that toss will not depend upon the previous results. Okay, if you have got heads, then the toss in the second event will not end up in getting tails or heads as dependent upon the previous event. So it means that the 2 events are independent of each other. Similarly, in third event, if you are tossing a coin again third time, the outcome of the third event, okay, will not depend upon any of the earlier event which has occurred. Okay, so what does it mean? It means that the 3 events are independent of each other, and if the 3 events are independent, we can write the probability of the 3 events like the probability of the first multiplied by the probability of the second multiplied by the probability of third. Okay, we know that the probability of a head is 1 by half 1 by 2 multiplied by, again the probability of heads is 1 by 2, and the probability of heads is again 1 by 2. Okay, so 1 by 2 multiplied by 1 by 2 multiplied by 1 by 2 is 1 by 8. This is the answer. Excuse me. Similarly, if you want to find out the probability of heads, and tails, how can you find it out? By using the independence of events. Okay, it's again very simple. If the 3 events are independent, so it means that these probabilities of these 3 events can be multiplied together and we get the answer. Okay, probability of heads is again half, probability of heads is half, and in third toss the probability of tails is again half. So 1 by 2 1 by 2 1 by 2 is 1 by 8. Okay, this is the essence. By writing all these probabilities in terms of the independent events, you can find the overall probability of any independent event. This is the essence of this question, and that's why I thought that it could be of your interest. So please do this question, and if you guys have any question, we will discuss it again. Okay, let's move on. So this is the remaining part of the question, and you can see that again other probabilities can also be found out by this method. So this was the question, and let's move on. Okay, now the very important topic of today is the sequential experiment. I have told you that there are basically two types of experiments. One is the sequential experiment, and the other one is the simultaneous experiment. Okay, so the reason of today's lecture that I am not delivering the lecture from slides but from a book is that I have some other ideas. Basically, sequential experiments are of two types, and mostly in slides you don't have any example questions. So today we will also discuss some example questions, their diagrams and so on. That's why I'm using the book today. The book reading is also recommended after this lecture. So basically, sequential experiments can be of two types. In first type, sequence of independent experiments will be discussed, and in the second type, sequence of dependent experiments will be discussed. Okay, when we will be discussing the sequence of independent experiments, we will have a probability law that is called binomial probability law. Okay, binomial probability law is a very important and very interesting probability law, and you will find it very helpful while solving many questions. So let's move on towards the binomial probability law, but first of all, see that what is the benefit of using the sequence of independent events. We have saw in our previous example that in any sequence of experiments, if you have the outcomes and all the outcomes are independent of each other, how can you find it out? You can just find out by multiplying the individual probabilities of each event. Okay, we have seen it in the last lecture, and the same thing is written here in this form. If you want to find out the probability of the independent events, sequential independent events, the probabilities can be found out by writing the product of all the individual probabilities, like the probability of A1 and A2 and A3 and up to AN will be equal to probability of A1, probability of A2 up to probability of A of n. This is the probability, and you can find it out very easily as we have seen in the previous example. Okay, moving on. This is the example, and this example is in this example what is asked is that you have to pick 10 random numbers from the interval 0 to 1. Okay, you have to pick 10 numbers, and if the event is like that you have 0 to 1, but there are some conditions related to this question. Find the probability that the first numbers are less than 1 by 4. Okay, the number should be less than 1 by 4, and the last 5 numbers are greater than 1 by 2. And let x1, x2 up to xn be the sequence of 10, or then the events of interest are. These events of interest will be this one. This is the first condition. This is the second condition, and as there are infinite numbers from 0 to 1 by 4, 0 to 1, and similarly from 1 by 2 to 1. There are basically infinite numbers, and you have to pick only 10 numbers. So how would you do it? First, you have to pick all the numbers which are less than 1 by 4. So what is the probability of getting any number from 0 to 1 by 4? That would be 1 by 4. Okay, initially you have got 1 by 4, then how many numbers are left? Again infinite numbers are left, because infinite minus 1 is again infinite. Okay, so you have to pick 5 numbers again, that would be 1 by 4. 2 numbers are gone, so infinite minus 2 is again infinite, 1 by 4, and multiplied by 1 by 4 infinite minus 4 is again infinity, and again 1 by 4. These would be the 5 numbers which are less than 1 by 4. Okay, why am I including 1 by 4? Because again I can tell you guys that there is no difference, almost no difference between 1.3.99999 and 1 by 4. This is a very slight difference, that's why I am considering it 4 as well. Similarly, these are basically the 5 numbers, and I can write it like 1 by 4 raised to the power 5. Okay, this is 1 by 4 raised to the power 5. Similarly, we have to pick the other 5 numbers from the interval 1 by 2 to 1. So what will be the probability? Again, the 1 minus 1 by 2 is 1 by 2. Okay, we have to pick it from 1 by 2 to 1. So what is the area? How much area do we have, or how much how many numbers will we have? That would be 1 over 1 by 2, and that would be 1 by 2 again. So again 5 numbers, similar method will be applied, and I will get 1 by 2 raised to the power 5, and that is the answer. Okay, you can see that these are basically the independent events. Picking one number does not depend upon the previous number, so that's why all the events are basically independent, and we can multiply their probabilities as well. Okay, let's move on. Okay, so this is the binomial probability law. Binomial probability law. What is binomial probability law? Binomial. Before diving deep into the binomial probability law, there is a term which is called Bernoulli trial. What is basically a Bernoulli trial? Suppose you are doing something, and there are 2 possibilities of doing anything. If you will be successful in doing that thing, or you will not be successful. It is another thing. You can also define some other steps in doing that thing, but in binomial law, or in Bernoulli trial, basically you have 2 things, success or failure. So if you are doing some trial and you have 2 possibilities, this is called Bernoulli trial. If you are tossing a coin in any cricket, in a cricket, if you are playing a cricket and you are tossing a coin, and you call heads as your side, that if heads come you will bat or you will win the toss. So heads mean basically success for you, and tails is a failure for you. Similarly, if you have considered tail as your thing, so that what will happen? Tail will be a success for you, and heads will be a failure for you. So Bernoulli trial basically cope with all these things, and Bernoulli trial basically considers what does it consider? It considers success and failure. Okay, so if P is the probability of success, and then what will be the probability of a failure? Probability of failure will be 1 minus P. Okay, that is the probability of a failure. If 1 by 3 is the probability of the success, what will be the probability of failure? That would be 2 by 3, because both of these will be summed into 1. Okay. Binomial probability law basically gives you the probability, total probability of any success. What is success? Anything you can call a success. Either sunny day is a success for you. Similarly, in communication system, packet toss is a success for you. So you can find the probability of the probability of losing 7 packets out of 100 packets. So getting 7 packets lost out of 100 total packets with some success, with some probability of error, will be your desired outcome. Okay. So how can we calculate it? Let's find it out. Example 2.37. In example 2.37, it is telling us that suppose that a coin is tossed 3 times. We assume that the tosses are independent and the probability of heads is P. Then the probability of the event of heads and tails is, that is the probability. Okay. These are the probabilities of heads and tails. This is the, if heads is the success, so heads, P multiplied by P will be equal to P cube. Similarly, the probability of heads and tails, because tail is now a not a success, but what? It is a failure. So that's why P multiplied by 1 minus P will be equal to P square 1 minus P. Similarly, heads will have this probability, tails will have this probability, and so on. You can see that in tails, what will happen? 1 minus P will end up in 1 minus P whole cube. So that would be the total probability of what? That would be the probability of this event in which we are not getting any success. Okay. The 3 tails are basically 3 consecutive failures. That's why we are considering it. So here you guys can see that the probability that we haven't got any success. What is K? K is basically the measure of a success, or measure of the Bernoulli trials, that we will get success. So if you don't have any success, what is that trial equal to? That is basically 1 minus P whole cube, and this is this one. Okay. Suppose you want to find out the total probability in these 3 trials, that you will get only 1 success. That would be equal to probability of tail, head, tail, and that would be this probability of this plus probability of this plus probability of this. Okay. I think you have got it, because now we can get only 1 head in each of these events. Okay. So why did we add them? Why didn't we multiply them? Because now here we have a term or. Either we can get this one, or we can get this one, or we can get this one. So if we are ORing it, we will add them, and after adding them, we will get this formula. This is 3p1 minus p whole square. Okay. Similarly, to find the probability of 2 successes, we will again add all the events in which we have 2 heads. Okay, because we are calling heads as our success. So after adding their probabilities, we will get this answer. This will be our answer. And if you want to find out the probability of 3 successes, their probability will be P cube, because this is the only term in which we have 3 successes. So you guys, I think you guys have found it out, that what is the essence of this example, and how can we find out the probability of any success in any Bernoulli trial. These are basically the sequential experiments which are independent of each other. Okay, in which in these three trials all the events are independent of each other. So this is the general discussion. Let's move on towards the mathematical equation for a binomial random variable. This is the mathematical expression for a binomial random variable. This is the mathematical equation for a binomial random variable. This is actually very easy. You may find it very hard, or it's very hard to understand in an initial or in a first look, but this is very helpful, very interesting, a very important formula. What is n? You have to, let's say you have to find out the probability of k successes out of n total number of trials. What is n? N is basically the total number of trials. What is k? K is the desired number of successes. Okay, similar thing you can write here, n choose k. This is the combination formula which we have seen earlier. What is p? P is the probability of a success, and k is the required number of successes you want to find the probability of. Okay, similarly 1 minus p would be the probability of the failure, and the exponent here will be n minus k, because n minus k will be the remaining events in which you are getting failure. So this is the formula. How to apply it, and how to apply it in this equation will be that, let's say you want to find out the probability of one success. Okay, if you want to find out the probability of one success, so writing n, how many number of different trials you have. Okay, you have basically 3 number of trials, and in these 3 number of trials you want to find out the probability of one success. Okay, this is 3 1. What is the probability of a success? That is p. And what is the value of k? This is 1. Similarly 1 minus p, and you have to write the exponent as n minus k. What is n? N is 3. What is k? K is 1, so here it will be 2. Okay, what is 3 choose 1? 3 choose 1 is basically 3 factorial divided by 3 minus 1 factorial, 3 minus 1 whole factorial multiplied by 1 factorial. Okay, this is p again, and 1 minus p square again. By simplifying this thing, you will see that that would be equal to 3. Okay, so if this is 3, you will end up with 3p 1 minus p whole square. This is the result for one success, and you guys can see that the same is written here. Okay, it means that you can find the probability of a success of any number of success out of any number of returns by using this formula. Okay. This is a mathematical form, and this is very easy. You can find it, you can use it anywhere. Let's move on and see different possibilities of using it and different scenarios. The n term, you can see that this is the same formula. Okay, this is the same formula, that this is the combinatorics. In combinatorics we use it, and this is the binomial coefficient. This is the binomial coefficient. Similarly, it will be this one which we have seen, in which regard the value of this is as 3. Please study it, and you will get all the understanding which is required. here this is the same formula. This is the same thing which we have seen for finding the probability of 0 success out of 3 trials, finding the probability of 1 success out of 3 trials, finding the probability of 2 successes in 3 trials and 3 trials again. The same thing you can find by using this formula. Okay, I have solved this thing for you. Please go ahead and solve all these things by yourself for your understanding. Okay, let's move on. This is the formula, and binomial probability law is also related with this one. Okay, let's see this question. This is example 2.39, and what is it asking you? Let K be the number of active non-silent speakers in a group of 8 non-interacting people. Okay, there are basically 8 people in a room which are not interacting with each other. Suppose that a speaker is active with a probability of 1/3. Any speaker is active with the probability of 1/3. Find the probability that the number of active speaker is greater than 6. Okay, you want to find out the if the number of interactive speakers or active speaker is greater than 6. You can basically make this question like this as well, that in a class of 8 students, the probability of asking a question of each student is 1/3. What is the probability that more than 6 students will ask a question? You can also write a question like this one. Okay, so how can we find out? We can see that the greater than 6 will be 7 and 8. Okay, either 7 people will ask a question or 8 people will ask a question. Okay, so we can find the probability that success is 7 or probability that success is 8, and we know the probability of a success. We can write it here. What are the total number of turns? That are 8. Similarly here we can again write here, and adding them you will get the answer. Okay, so this probability law is very important, very easy, and you can apply it anywhere, wherever you want. You can apply it, you can get your answers, and this thing is very important and very easy. I am ending this lecture here. I will see you in the next video, where we will discuss more opportunities and more problems related to the binomial probability. Okay, stay tuned please. Thank you.